Thank you very much, and thank you, everyone, for the wonderful collaborations that we've had here in the Siemens framework. So today I'm going to talk about turnstiles and topological index in fusion reactor divertors. So let me start with a little bit of a story about my favorite mathematician of all time, Henri Poincaré, who is basically the father of dynamical systems. And it's quite a while ago. In 1899, he wrote a book, Les méthodes nouvelles de la mécanique céleste, in which he laid the groundworks of dynamical systems and analyzing trajectories, and Poincaré plots came from there. But he also made a very frightening observation in that book, and that is if you have a three-body problem, it is generally chaotic. So if you have the Earth passing around the sun, and it's perturbed periodically by Jupiter's mass moving around at different frequencies, then that could be chaotic. And so that laid a deep existential fear, like when will the Earth be flung into the dark depths of space because of that? Now, it took more than half a century before Kolmogorov, Arnold, and Moser were able to lay those existential angsts to rest, because they figured out that under small perturbations and under certain conditions, there exists invariant tori. There exists, like you have your phase space in which your Earth is orbiting the sun, but in between the space of that orbit and a position in that space where the Earth is far away, there exist invariant surfaces in that phase space that limit the motion of our Earth's trajectory far away from those scary places. So understanding transport through chaos can not only alleviate our existential fears, but it can also be used to analyze magnetic fields in fusion reactors. So the magnetic field in a fusion reactor can also be described by a Hamiltonian dynamical system. And this case, a 1.5-dimensional one. David Feverly last year had a few observations to make that that's not always true, but we can at least draw these beautiful Poincaré plots that show chaos and connectivity between different areas in phase space. So it was indeed, as Mies told you in the beginning, last year that I had a conversation with him about another method to analyze transport through such a chaotic region. And that is the turnstile mechanism that gives limits to how fast a particle can go from one position in your space to another position. And so now I went back to work, and I worked really hard on it. And then a year later, now we can calculate that exact quantity in fusion reactor fields, and specifically also in stellarator fields. So let's have a little bit of a look at the stellarator. We have magnetic surfaces in the center. Oh, that's not how this pointer works. Yeah, that are all neatly closed orbits. And the plasma, to first order, follows those field lines. So in a plasma, the perpendicular transport, the rate at which particles move perpendicular to field lines, can be orders and orders of magnitude higher than their parallel transport. Sorry, that was the wrong button. And so, yeah, this orbits, these trajectories of the field lines can tell us how our heat moves through the device. So here in W7X, we see an island divertor. It has in the top, this is a standard configuration with an island divertor, but we also have chaotic configurations here. This is the W7X GIM configuration, which we have a chaotic field in the edge. Now, a few notes in the beginning. I will not be talking about, there's a lot more going on in a plasma. I will not be talking, for example, about turbulent transport, neoclassical effects, particle orbits. I will firstly just assume the magnetic field and transport of field lines through island chains and around in the edge of a stellarator divertor. So let's start with some preliminaries and define the Poincaré section, or the field line map. You do that by taking a point, here the point X, and you follow the field line all the way around the torus until it reaches the same plane. That can also be a symmetry plane in a stellarator, and you map where it ends up, f of x. Now, such a field line has fixed points. So the fixed points are the field lines that when they go around the device, they come exactly back in the same place. So the magnetic axis is an example of a fixed point. That's a fixed point of the one-period field line map, but there can be other field line, higher orders of the field line map. So a magnetic island is, for example, a fixed point of the 3 map you applied. Period 3 island is a fixed point of the 3 map. You apply the map 3 times, and you get back to where you started from. So we can analyze these fixed points using like the linearization of the mapping around the fixed point. So we ask, if we take a little step in R and if we take a little step in Z, how does FR, how does FC change? Now what we get is a 2x2 matrix with real coefficients, because we all differentiated with real qualities, that linearly describes to first order the effect of that mapping. Now that matrix is actually quite constrained because of another effect that the divergence of B is 0. All of the field lines can't converge or diverge from it. That's encoded in the determinant of the mapping. So this matrix has to have determinant 1. And that makes it part of a well-known group, the special linear group of order 2 over the reals. Now, that doesn't say much to everyone, but if you look into the literature, that group has 3 subsets. So it's all classified by the trace of the matrix. If the trace is larger than 2 or smaller than -2, the fixed point is hyperbolic. We get what plasma physicists call an X point because of the shape of the trajectories around such a fixed point. If the trace is exactly 2, we get an intact surface. So there's a line of points that all map to themselves. This is, for example, in a rational surface. Every field line after a certain number of times around ends up exactly where it is. But if you're above it or below it, the magnetic shear is faster, the rotational transform is faster or slower, and we can't this kind of shear. And then the third option is the elliptic fixed point, in which the matrix is basically a kind of rotation matrix. Here I wrote the matrix for a rotation of pi over 3. And every point maps to invariant circles or ellipses around the fixed point. Now, these X points are very interesting because they form a sort of natural diversion. So we can first talk, if we have that fixed point, the trace is larger than 2, then we can talk about the eigenvectors of that matrix. So because the map is basically like f of x plus delta x is f plus that matrix times delta x. If you're along an eigenvector, you get an eigenvalue times that eigenvector. So that's the direction in which you either move further and further and further away, the red line, or closer and closer and closer, the blue line. Now, if you're slightly to either side of it, so if you're slightly below it, you will end up down. And if you're slightly above it, you will end up to the top. Now, that line, linearly, it's the span of that eigenvector, but it actually extends all the way much, much further. And it still forms a kind of barrier between the points. If you're on either side of that line, you don't cross that line. You follow it kind of along the matrix, along the manifold is what these lines are called. And then when you reach the X point, you either go to one way or the other. So this is kind of like a hill crest in a watershed. Everything on one side goes into one river, everything on the other side goes into the other river. Now that manifold is therefore interesting as a kind of barrier between different regions. Yeah, and that's why, because of that splitting of trajectories around an X point, that we often use these to design our divertors. So in a tokamak, we have a plasma current running through our closed magnetic surfaces, but we place a coil underneath that creates an X point in between. And so the heat that is loaded onto the separatrix is diverted, and that creates a separation between the plasma and our plasma-facing components. Now, in a stellarator, we use the X points in an island chain around the plasma in order to create that diversion. And these are not axisymmetric anymore. These X points rotate around as you go around the device, but they still form this kind of good diversion where you can separate your wall from your plasma. Now, there's a third option for something like LHD, which has two helical coils that rotate around each other. You create a region of closed surfaces and two X points around it. Now, this ideal picture is, of course, a nice cartoon to draw. But in the real world, in a tokamak, when you add a resonant magnetic perturbation or something, you can often get stochasticity in the edge. We also before looked at the W7X gym configuration, which has a stochastic region around. And in LHD, we have those also naturally a stochastic region around our closed flux surfaces. So let's look a little bit at what is possible in such a divertor by looking at the topology in the edge of our fusion devices. So we define a thing called a topological index. So the topological index is calculated from a curve that encloses a fixed point. And it's basically the winding number of that curve. I won't go into the full details on how you calculate it, but you can do that for any curve. And the important thing is O points have the opposite topological index from X points. So if we can do that for a circle enclosing one null, but we can also look at the entire device and look at how many X points are there, how many O points are there. Now, when we do that for most type of devices, we see that we have an O point there at the magnetic axis, we have an O point at the tokamak coil, and we have an X point in between. So that total sum, the total number of X points minus the O points, is 1. Even in the chaotic LHD configuration, we have an island chain with an equal number of X points and O points. They'll all cancel. And what we're left is the magnetic axis. So most configurations, if you look at the total index of the field that maps, it is +1. But for example, we also already looked at the LHD configuration here. It has 1 O point, but actually 2 X points. So that one doesn't fit that mold. There are unpaired X points in that configuration. And there's the 2 coils running around it. They have something to do with that. But yeah, we wanted to look at, are there other configurations in which that happens? So this is a fun project that I did together with Bob Davies. And we looked at the total topological index of stellarator configurations from the Quasar database. So if you look at the configuration here under consideration, there's a bunch of points that the field lines do lie on these neat and nested surfaces. And there's the O point inside of there. But we can also construct the maximal contractible end mapping set. So not all field lines make it around, but we do limit ourselves to all field lines that do make it around. There's a region here in phase space that does make it all the way around the device. And then on that boundary, we calculate the topological index to know how many X points and O points there are inside of that region. And when we look at that, we find a winding number of -1. Again, a configuration where we have 2 more X points, 2 X points, and only 1 O point. And we can see that the manifolds emanating from these X points, they go out to the coils. So that is already a very interesting configuration. We searched this a bit further, and everything is in this paper. Davies, Bob was the first author of it. That's on arXiv. We can find very interesting edge topology configurations in the fields in the Quasar database. So Quasar wasn't optimized for the field around the surfaces. It only considered the surfaces. But once you add coils to it, the field starts doing funny things around it. And here, this configuration I also want to talk about a bit. It has a period 4 island chain, but there's also a period 1 fixed point there, whose manifold, so this point stays on the outside, but its manifolds reach out like that. So you have also another interesting possibility. So looking at the topology of the field line maps allows you to find interesting configurations. So now let's take a step back and talk about these maps and turnstiles. So first, let's look at the 3 types of maps that I will be discussing today. So the simplest form of a map is an iterated map. You don't have to do that complicated 3D tracing, but it's just a function from 2 coordinates, x and y, to another 2 coordinates, x and y. And under certain conditions on those functions, you get trajectories that are very similar to Hamiltonian dynamical systems. Mies used the standard map. You can also start working with analytical fields. That's what we'll do after. So these are two-dimensional fields described by a flux function from which we calculate the field, and then we integrate that. But because we're working with analytical functions, everything behaves nicely, and we can add perturbations to see the chaos. And then in the last step, we will go to fully three-dimensional fields, where the magnetic field itself is not a neat analytical expression, but it's sourced by a set of coils on which we calculate the Biot-Savart in order to find the magnetic field at any point and do our field line integration. So let's start simple. I know I'm talking pretty fast. Let's start simple with the iterated map. And where Jim Mies used the standard map, I will talk about the token map, which is described in a few papers by Balescu, Flat, and Spineanu. So the functions, I won't go into full details, but it's pretty easy for a computer to calculate the sines and cosines and get from every point to a new point. So the two variables here are theta and psi. These are named because of their analogies in, for example, a fusion reactor. Psi can act as a flux function. Theta is a periodic toroidal angle. And when we look at the trajectories in such a map, so we construct a Poincaré map by following 6,000 iterates on each trajectories along a line. And then we see that we do get, at psi is 0, neat closed surfaces. They're a little bit twisted depending on how much chaos you add. But as we go out, we get into a very chaotic region. So in that chaotic region, we can ask the question, what does it take for a field line to go from the plasma side out to the wall? How can it move there? So here we have the hot plasma side, and up on the top of the picture, we have the cold plasma side. First things that we do is find the fixed points of any island chain in that region. So there's a period 3 island shown in blue, period 5 island shown in red, and a period 2 island that I show with green dots. Now, we can go back to showing those manifolds that form these kind of barriers where a fixed point has to go all the way, a field line closer, it has to go all the way to the x point to decide whether it goes up or down. Now here we see the island chain for the first, for the manifolds for the first island chain. Here we see the manifolds for the second island chain. And here we see the manifolds for the third island chain. Now I know there's quite a lot on this slide, so let's focus on one single occurrence of this island. So we zoom in here, and we're going to follow the trajectory of a region here in this Poincaré plot. So every point here, you calculate where it goes to, and then it will end up in a new place. So here, because it's a period 3 island chain, we apply the 3 map. So we start with this region, and if we look at where it came from, so we go 3 steps back, it actually came from exactly there. So because the manifolds map to themselves, that region also has to be contained by the manifold. If we go 1 step back, it came from here. If we go 1 step back, it came from here. So every single trajectory in that region maps to another. If we go forward, it maps to there, there, and there. So we can see that this is a bunch of flux lines that go from one side of the island, from the plasma side, and they end up in the island region. Now, of course, there must be an equal area that I show here in gray that, upon the same mapping, goes instead from outside in, it goes from inside out. And that is why Jim Mies called this a turnstile. This is the best figure that artificial intelligence could come up with, but it lets a fixed amount of trajectories in through the border and a fixed amount of trajectories out. So I would call it more like the turnstiles in a subway that ensure that the total number of the flux of people in and out is the same, but it happens distributed over the entire line, so to say. Once we have passed through the turnstile from the plasma side inside, there's an equal area. No, there's not an equal area. There's another turnstile that we need to pass through. So let's look at that one in green. If we look at where it came from, there's even some overlap with the turnstile on the inner separatrix, or the broken separatrix, the inner homoclinic connection, into that turnstile on the outer. And if we look where it goes to, in the end, after it's gone all the way to the other x point, it has decided, I'm now on the outside. So this is kind of the path that a portion of phase space, a bunch of trajectories, need to take to pass such an island chain. And therefore, such an island chain can form a barrier to transport through such a chaotic region. So there's another thing that you can do with these manifolds. There are some special trajectories on here that can't decide whether they are in or out of the subway. These are called heteroclinic trajectories. These are the trajectories that, in one limit, go to one of your x points, and in the other limit, they asymptotically approach the other fixed points. We can calculate them for both the top, the bottom manifolds, and these will be important later. So now let's look at the perturbed tokamak. So we go one dimension up in complexity, or one step up in complexity. We describe an axisymmetric field, the way that tokamak physicists usually like, with a flux function. That's a very simple flux function. It's just circular surfaces. We just choose a specific toroidal field such that we get a rotational transform that we like. Now, to that simple configuration, in which all of the field lines lie on nested surfaces at constant psi, we add another bit of field. We add a separatrix coil right there, from which we have analytical expressions. Those who like elliptic integrals can eat their hearts out when calculating this. Yeah, I won't go into that. If we add that separatrix coil, we get a very tokamak-like configuration in the magnetic field. We get an X point in between the coil and the plasma. Now, we can add to that a perturbation as well. This one is non-axisymmetric. And we also do that in the simplest form. So we don't do perturbations to the Hamiltonian. We just add a magnetic field that is divergence-free, that has toroidal mode number 1 and poloidal mode number m. And m is here 6. So that means that the field pushes in, and then pushes out, and pushes in, and pushes out 6 times as you go. And that entire perturbation rotates exactly once as you go all the way around the torus. Now we add some sort of radial distribution to it. We don't want it to blow up at infinity. So there's a Maxwellian-like radial distribution. But you can see from the size of the vectors that, yeah, it has around a significant amplitude around the separatrix. It's 0 at the magnetic axis. So we can look at the effect of adding such a perturbation, starting from 0 perturbation. And we can see that as the perturbation increases, we add a lot of stochasticity, but we also see the manifolds grow and get bigger and bigger, and that correlates with the amount of chaos we have. So what we want is an efficient algorithm to calculate the turnstile flux, the area in one of these lobes, because that quantifies how many field lines are interchanged between the plasma region and the outside as we go around the tokamak poloidally. So this is where my conversation last year with Jim Mies came in. He showed me a paper and a very elegant method developed by Mies, McKay, and Percival in order to calculate the amount of flux in such an area. So the simplest thing that you could think of doing is just to find that boundary here on the manifolds. So you find gamma n and tau n, and then you integrate a dot dl along that. But that's an expensive thing to do because you need a large number of points on gamma n and tau n, and you need to integrate them all the way from your fixed point. So is there a neater way? You first need to find those homoclinic trajectories anyways. And so what Mies, McKay, and Percival came up with is that you don't need to resolve the entire manifold. You just need to find those 2 field lines, those 2 trajectories, those 2 homoclinic trajectories. So I'm calling hetero and homo. For those who are a bit confused by now, I apologize. They're the same thing, except that a heteroclinic trajectory has 2 fixed points, and a homoclinic, the manifolds from a fixed point go back to that same fixed point. But the math for it is all the same. And they show that instead of having to calculate the complicated turnstile, just find those two trajectories. Then as you go around the torus, you integrate A dot dl along them, and all the way from the x point back to the x point. And if you take the difference of those two integrals, you get the turnstile area. I have this also in more pictures at the end of my presentation if someone wants a more in-depth presentation. But yeah, so with this, we can now calculate the turnstile area in this toy model here. So we increase the amplitude for that n equals 6 mode. We see that the turnstile area increases. We can also do this for other modes. So we do this first for the m equals 6 mode, but for the m equals 4 mode, we see something similar. The island structure is very different, and the slope of this line, as we increase the perturbation, is also different. Different perturbations have different effects on the chaos. So I normalize the magnitude of my perturbation to the magnitude of the axisymmetric field. And at the very right of the graph, we actually have pretty high amplitudes of about 6 up to 10% of the axisymmetric field strength. So are we even talking about a perturbation at that time? But the calculation of the manifolds, the action principle by Mies, McKay, and Percival, still works really well. We can calculate these turnstile areas for hundreds of different perturbations up to very high amplitudes and crazy manifolds like this. So what I'm showing here is from top to bottom, I'm increasing the perturbation strength. And from left to right, I'm increasing the poloidal mode number. So different mode numbers have different effects also on the field inside of the tokamak, but also on the shape of those manifolds. I think this is an interesting tool to, for example, optimize your RMP coils, and you can get an actual number of how effective it is on how much of a turnstile area a given amount of current achieves in your tokamak. But tokamaks, they're axisymmetric. The perturbations are just slight changes to it, maybe some bigger changes. What we really want to get into is stellarators and turnstiles in stellarators. So as I said before, we now have to calculate the field using a Biot-Savart integral on the coils. And this is quite a bit more expensive than evaluating those analytical expressions. Now, furthermore, we have some of the problems that not all field lines pass all the way around the device, so we have to also deal with what we do if we get a field line that escapes to the coils. But we fixed all of those problems, and we have looked, again, at a bunch of configurations in the Quasar database. Thank you, Andrew, for making such a beautiful tool. These are the two that I'm going to be looking at. One that is more similar to W7X with a large island chain in the edge, and one that is quite crazy with a very big